Hi, Tutor. My name is Peter by Group 10. Today I would like to present the fruit assignment 2. So this is our group member and Amelia, Chuan Heng and Mama Ali bin Muhammad Fatih.
My name is Muhammad Ali bin Muhammad Fauzi. My metric number is B1323103995. We talk about what is CDF. CDF is the computation fluid dynamics. It's a branch of engineering and physics. They use numeric method and algorithm to analyze and solve the problem involving fluid flow. It allows researchers and engineers to simulate the behavior of fluid and liquid and gas, and their interaction with surface or the fluid in a visual environment.
Hi, my name is Wu Chuanheng. I'm going to talk about the theory related to our topic. First is the boundary layer theory. Boundary layer formation, fluid flows over a stationary surface and velocity increases from zero at the surface to free stream velocity outside the boundary layer. And the second one is the Blaser solution. Blaser solution analytical model for steady, incompressible laminar boundary layers and uses similarity variables to simplify Navier-Stokes equation. And third one is the flow characteristic. It's initially laminar, smooth and orderly. Transitions to turbulence further downstream. And second, I want to talk about the problem. First is analyzing the velocity profile. The velocity profile within the boundary layer changes with airflow velocity due to variation in shear stress and viscous forces. Low airflow velocity at lower free stream velocities, the fluid momentum is weaker, resulting in a more pronounced effect of viscous force. At high airflow velocity at higher free stream velocity, the momentum of the fluid dominates, reducing the relative importance of viscous force. Second is the boundary layer thickness. The boundary layer thickness decreases with increasing airflow velocity. Low airflow velocity, the lower momentum result in slower momentum diffusion away from the surface. This allows the viscous effects to dominate over a larger region and increasing the boundary layer thickness. At high airflow velocity, increased momentum means the viscous force are relatively less effective at slowing the fluid near the surface. This leads to thinner boundary layer as the velocity rapidly approach the free stream value.
Thank you, Fu Chuan Heng. Next, I will present about geometry detail and dimension and method of simulation. Firstly, I will click the flow fluid and drag it into this box to generate the simulation. After I generate, I will save this file under any file, name it as model. Until it's finished. After it's finished, then I right click on this geometry and click on this new design modeler geometry. After it's come into this window, firstly, I will click on this Z axis because we want to generate in XY plane. Then click sketching, setting, go to the grid and turn on the show in 2D and snap. Change measure grid spacing to 0.1, press enter. Change minus step per measure to 10, press enter. Next, click on draw. We will draw an rectangular. We'll put it around here. Then we will use dimension. Because of our group is group 10, so I change the value of the dimension H2 and V1 to V1 equal to 1.5 meter and H2 to 0.3 meter. After I change the dimension, I click on concept, surface from sketches, and I click surface of the object and click apply. Then click generate. After you click generate, it will become gray color like this. Then you can save the file, save the project. We can close the geometry window and come out here. Next, we will do mesh. Click on mesh. Here's the window. Click on Z axis. Firstly, we click on mesh, and first we will do face meshing. We click on face meshing, which is this, and click on surface. Click on the surface and press apply. After press apply, press generate. Next, I will insert edge. I will right click on this mesh and insert edge sizing. By clicking this edge button and use control button, push control button and hold it, click upside and downside, you will get to edit both sides at the same time. And you change the type to number of division, set it as 50, and change the behavior to hard. After that, insert another edge sizing at this edge. Change the type to number of division, set it as 60, behavior is hard, and bias type is like this. Then bias factor is 70. Also the same for the back side of the rectangle, but the number of division here we change as 60, and behavior as hard, bias type like this, and bias factor at 70. And we apply reverse bias on this side. Next, we will assigning name for each surface and edge. Firstly, I will assign in this surface by clicking this surface button and click on this, right click on it, and create name selection. After create name selection, I will name the surface is airflow. After that, I will click on edge button and choose this side and right click and do the same thing and set it as inlet. This side is outlet, bottom here is plate, and up here is far field pressure. After done assigning name, save. Then we need to save the project. Click the save project and click out from the window. Next, we will do the setup. Double click on the setup. Set this as double precision, and solver processor also can set as S1, or you can check by your task manager and check your CPU performance. And click start. After we inside this window, we will see this mesh of our simulation. Firstly, I will change these models. Left click on this model and click on this lamin viscose and change it to lamina. Press OK. Then I will go to material, press on fluid, left click on it. Okay. I'll change this density to 1 and viscosity to 0.001. Change grade and close. After that, I will go to method, double click on it, and change this scheme to simple. That's all. Then I will go to residual, double click on it, and change it to a small decimal for precise monitoring. I change it to 1 power 10 minus negative 6. The change of these three. Then I press OK. Next is I go to initialization. Change this method to standard and compute form inlet. Press initialize. Or before that, change this to velocity of 2.5. I change it and press initialize. One more is we need to change here inlet velocity. Here I will change the velocity magnitude is 2.5 meter per second, and as component of flow direction I will change to 0.15 because of line of plot of our group is at the middle of simulation, and our long is 0.3, so at middle is 0.15. Press apply and close. After that, I will run calculation. Increase the number of irritation to 1 million. After that, press calculate and wait for the result.
So I will talk about the result. So this is the first result, and then the graph. This is the residual plot. So this graph shows the residual for quantity as velocity and y velocity as a function of the number of iterations. So the second image is about the best and solver setup. The next image is for about the velocity vector plot. So you can see this the red arrows to talk about the indicate the velocity directions. So the color scalar is talk about the represent the velocity magnitudes per second with red indicating higher speed and blue indicating lower speeds. So and then the dish is mesh is talk about the new condensed type line domain use define and others which allow use to set up and control the simulations. This image also to talk about the visualization pipeline. So the main plot on the right display pipelines current by velocity magnitude. Use the unit by the meter per second. And then this image like the 3D photo. This interface is like being used to validate the setup of quantity conditions, like the computation domain and prepare report for analysis. The interface will be in the early stage of post-processing or domain instructions. This is the second graph to show the line in the plot and convergence trends. So then this image is show the mass quality, velocity profile, and distribution cell. Then this also go to the steady flow and non-state boundary condition and flow directions. Then this image also show the uniform flow. Then the red region indicate a steady and uniform velocity field, which is typical for fully durable flow in the simple geometrics. This is the flow uniformity. And then the straight and evidence page outlines are just a well-durable terminal flow field. Then this is the second result for the 3D photo. Then it will show you about the ensure the solution domain is set up for every then identity boundary condition and flow region of the rest. As is post-process result by generating report and is ready to understand the simulation perform. So that's all for my part.
One of the most important parameters in FT dimension is flow velocity. It determines how quickly air flow across the area under computation. The airspeed at a given position in the system is simply described by velocity of 1 meter per second and 2.5 meter per second. 1 meter per second is a competitive flow velocity, suggesting that the flow may be less energetic or more laminar. It could be happen in the area of the domain where friction with solid boundaries or viscous forecast effect flow. For 2.5 meter per second, D is the higher velocity indicate a flow that is more dynamic. It could be stand for a place where air accelerate like Indah with smaller opening or by geometric construction which cause air to move faster. The geometry of the system and boundary condition cause a flow velocity to vary within domain in many FT equation. A variation in speed between 1 and 2.5 meter per second is acceleration. As the air pass through the system, it can be acceleration. This may be caused the flow method has contracted, for example, through the duct narrowing or nozzle, requiring the same amount of air to pass through the smaller space and speeding up the airflow. Prevention of the mass continuity equation for incompressible flow, it requires that the mass flow rate be keep constant. This implies that in order to maintain the same flow rate, the velocity must rise if the flow cross-section area decrease.
So now I'm going to talk about the effects of different airflow velocity. For velocity profile, if low airflow velocity, the boundary layer thickness increase due to slower fluid acceleration near the surface, and the shear stress, surface shear stress reduce, leading to flatter velocity profiles. Transition to the turbulence will delay as lower Reynolds number promotes stability in laminar flow. If high airflow velocity, the boundary layer thickness will decrease as the higher velocity promotes faster fluid acceleration near the surface, and the shear stress surface increase due to steeper velocity gradient near the surface. And the thickness is the boundary layer thickness. The higher airflow velocity reduce boundary layer thickness due to stronger inertial force dominating over weaker force, leads to thinner velocity profiles and sharper velocity gradients near the surface. In a lower airflow velocity, increased boundary layer thickness as because forces dominate, result in smoother velocity transitions and thicker profiles. And why it happens in lower airflow velocity? Because forces dominate, slowing fluid acceleration and the boundary layer thickness as momentum diffuses over a larger region. And the momentum diffusion, what will happen at lower velocity? Because force dominate, causing momentum to diffuse over a wider region. And at the higher velocity, inertial forces keep fluid momentum localized, tightening the boundary layer. Thank you.